Water moves in silence before it speaks. Beneath the surface of every river on Earth, a drama of physics unfolds that has shaped continents, seeded civilizations, and written the oldest stories humanity has ever known. From the torrential whitewater of mountain headwaters to the languid, mirror-dark meanders of coastal deltas, rivers are not passive features of the landscape. They are living systems, metabolizing sediment, carving stone, hosting ecosystems so intricate that scientists have spent lifetimes describing only fragments of them. The flow of a river is governed by laws as precise as any in mathematics, yet the results are endlessly complex and endlessly surprising. Rivers are also archives of geology, of climate, of human ambition and human folly, carrying evidence of events that occurred long before any instrument existed to record them. What you are about to witness across the coming hours is not simply a tour of famous waterways. It is an invitation to see rivers as they truly are, ancient engines of planetary transformation, carrying within their currents the dust of mountains, the dissolved memory of glaciers, and the faint chemical signatures of rainfall that fell before any human eye existed to observe it. At the heart of river science lies one of the most elegant distinctions in all of fluid dynamics: the difference between laminar and turbulent flow. When water moves slowly and in orderly parallel layers, each molecule gliding past its neighbor without crossing over, the flow is described as laminar. It is almost dreamlike in its smoothness, a thin film of water sliding down a pane of glass, or the near-still surface of a very deep, slow river. But rivers rarely remain laminar for long. As velocity increases, or as the channel narrows, or as the riverbed roughens with boulders and gravel, the orderly layers collapse into chaos. Turbulent flow erupts in swirling eddies, cross-currents, and vortices that mix the water column completely. The transition between these two states is described mathematically by the Reynolds number, a dimensionless ratio comparing the inertial forces in a fluid to its viscous forces. In most natural rivers, the Reynolds number climbs well above the threshold of 4,000, meaning that true laminar flow is almost never found in the wild. Rivers, by their nature, are born turbulent, and it is in that turbulence that so much of their geological power is hidden. The Reynolds number, named after the Irish-born physicist Osborne Reynolds, who formalized it in 1883, does more than classify flow patterns. It reveals the hidden architecture of how rivers accomplish their geological work. A fluid with a low Reynolds number is dominated by its own internal stickiness, its viscosity resisting any tendency toward disorder. A high Reynolds number indicates that inertia has overwhelmed viscosity, and the fluid becomes unruly, folding back on itself in three-dimensional spirals called Kolmogorov eddies, named for the Soviet mathematician Andrei Kolmogorov, who in the 1940s described how turbulent energy cascades from large swirling structures down to microscopic ones before dissipating as heat. This energy cascade spans many orders of magnitude, from the broad river meanders visible from the air down to vortices invisible to the naked eye. In rivers, the energy cascade is not merely a theoretical curiosity. It is the mechanism by which water accomplishes the extraordinary feat of lifting sand grains, rolling boulders, and suspending fine clay in a continuous cloud throughout the water column. Every grain of sediment a river carries owes its journey to this precise, invisible mechanism. Deep beneath the surface of any large river, the riverbed is never truly still. Even in rivers that appear placid from above, a constant process of sediment transport churns at the interface between water and substrate. Scientists distinguish between bedload, the heaviest particles that roll or skip along the bottom, and suspended load, which consists of finer particles held aloft by upward turbulent currents. There is also wash load, particles so fine that they remain suspended almost indefinitely, coloring the river brown or red or gray depending on the geology of the watershed. The suspended sediment concentration of the Yellow River in northern China, known as the Huanghe, is among the highest ever measured in any natural waterway. During flood season, the river carries such extraordinary volumes of loess, a fine wind-deposited silt, that it achieves a density closer to flowing mud than to water. This sediment is so abundant that the river has raised its own bed over centuries of deposition, creating a phenomenon where the channel now flows above the surrounding floodplain, held in place only by millennia of human-built levees. The Yellow River's relationship with silt is inseparable from one of history's most consequential and catastrophic patterns. Over 4,000 years of recorded history, the river has changed course dramatically at least 26 times and caused catastrophic floods more than 1,500 times. Its lower reaches historically shifted between outlets hundreds of kilometers apart, sometimes draining northward into the Bohai Sea and sometimes turning south to join the Huai River system before reaching the Yellow Sea. Each course change transformed entire agricultural regions overnight, burying fields beneath sand and converting others to swamp. The river's Chinese name, Huanghe, literally translates to Yellow River, a direct reference to its perpetual sediment burden, which gives the water a thick, opaque, ochre coloring unmistakable from any vantage. Ancient Chinese civilization did not merely live beside this river. It was organized around the challenge of managing it. The office of hydraulic engineer was among the most powerful in imperial bureaucracy. The failure to control the river was sometimes interpreted as evidence that a dynasty had lost the mandate of heaven, making flood control not merely a technical enterprise but a theological and political one simultaneously. Where the Yellow River civilized northern China through its terrible unpredictability, the Nile River civilized northeastern Africa through its legendary regularity. Every year, without fail, the Nile flooded its banks between June and September, depositing a fresh layer of rich black silt. The ancient Egyptians called it Kemet, meaning black land, across the floodplain. This annual gift of fertility made the Nile Valley among the most productive agricultural land on Earth despite being surrounded on all sides by desert. The Egyptians measured their calendar not by the stars alone but by the river. The year was divided into 3 seasons: Ake, the inundation; Perate, the growing season as the waters receded; and Shimu, the harvest. The Nilometer, a graduated stone column or staircase built into the riverbank, was one of the oldest scientific instruments in human history, allowing priests and administrators to predict the harvest yield from the flood level months in advance. A flood too shallow meant famine, a flood too deep meant destruction, a flood in the ideal range meant abundance, and abundance meant taxes could be collected and monuments could be built. The ancient science of measuring the Nile was remarkably sophisticated. Nilometers were constructed at multiple points along the river from Aswan in the south to the delta in the north, creating what amounted to a distributed hydrological monitoring network spanning nearly 1,000 kilometers. Records of flood levels at the Rhoda Nilometer in Cairo extend back more than 13 centuries, making it one of the longest continuous instrumental records in scientific history. Hydrologists and climate scientists have analyzed this archive to extract information about historical droughts, El Niño events, and long-term changes in the monsoon systems feeding the Nile's 2 main tributaries, the White Nile and the Blue Nile. What those records reveal is a river of extraordinary sensitivity to distant atmospheric conditions. The Nile's flood levels respond to rainfall patterns as far away as the Ethiopian highlands and the East African Great Lakes region. The readings at these ancient stone instruments encoded the rainfall record of half a continent. In this sense, the ancient Egyptians standing at their Nilometers were, unknowingly, reading one of the earliest and most comprehensive climate data sets ever assembled, expressed in the rising and falling of a single river's surface. The distinction between the White Nile and the Blue Nile reveals a fundamental truth about how large river systems are assembled. The White Nile originates in the Great Lakes region of equatorial Africa, flowing northward from Lake Victoria, the world's largest tropical lake, in a long, relatively gentle journey across flat terrain. It contributes a steady year-round base flow to the main Nile, sustaining the river even during dry months. The Blue Nile, by contrast, emerges from Lake Tana in the Ethiopian highlands and carries the violent energy of the highland monsoon. During the Ethiopian rainy season, the Blue Nile swells to more than 50 times its dry season volume, carrying enormous loads of red-brown sediment scraped from volcanic soils. This sediment, not that from the White Nile, is the primary source of the fertile silt that made Egyptian agriculture possible. The 2 tributaries merge near Khartoum, Sudan, their waters visibly distinct for many kilometers downstream before finally mixing. For millennia, no one in Egypt knew where the flood came from. The source was mystery. The gift was everything. The search for the source of the Nile was one of the great obsessions of European exploration in the 19th century, sending expeditions into the African interior that were simultaneously acts of genuine geographic curiosity and instruments of colonial ambition. The debate between Richard Francis Burton and John Hanning Speke as to whether Lake Tanganyika or Lake Victoria was the true source generated fierce public controversy in Victorian England, culminating in a formal debate scheduled for September 1864 that was cancelled when Speke died in a shooting accident the day before it was to take place. What the debate obscured was an insight that modern hydrologists now consider obvious. Large rivers do not have single sources. They have watersheds, entire networks of smaller streams and tributaries that collectively drain a defined region of land. The Nile watershed covers approximately 3.4 million square kilometers, encompassing parts of 11 modern nations. Every raindrop that falls within that watershed and eventually reaches the sea passes through some part of the Nile system. In this sense, asking for the source of the Nile is like asking for the single origin of a forest. The concept of the watershed, also called a catchment or drainage basin, is arguably the most important unit of analysis in fluvial science. Watersheds are separated from one another by topographic divides, ridge lines and high points across which water flows in opposite directions. The continental divide of North America, running along the spine of the Rocky Mountains, determines whether precipitation drains eastward into the Mississippi-Missouri system and eventually to the Gulf of Mexico, or westward into the Columbia, Colorado, and other Pacific draining rivers. But watersheds are not merely static containers. They are dynamic systems in which land use, vegetation cover, soil permeability, and geology all interact to determine how much precipitation becomes runoff and how quickly. A watershed covered with forests absorbs rainfall slowly, releasing it gradually into streams over days and weeks. A watershed stripped of vegetation and covered with impermeable surfaces, pavement, rooftops, compacted agricultural fields, converts the same rainfall into rapid, concentrated runoff that can overwhelm river channels within hours of a storm's onset. This hydrological difference has profound and measurable consequences for flood risk, groundwater recharge, and water quality in every river draining these transformed landscapes downstream. Perhaps no river makes the power of its watershed more visibly apparent than the Amazon. Draining approximately 7 million square kilometers, nearly the entire northern half of South America, the Amazon River system moves more water than any other river on Earth. At its mouth near the Brazilian city of Marajo, the Amazon discharges roughly 209,000 cubic meters of water every single second, a volume that represents approximately 20% of all freshwater entering the world's oceans from rivers. The sheer scale of this discharge creates a freshwater plume detectable in the open Atlantic Ocean hundreds of kilometers from the coast. The Amazon's power derives not from extreme elevation. Its headwaters in the Peruvian Andes are certainly lofty, but the river traverses a vast, nearly flat basin for most of its length, but from rainfall. The Amazon basin is one of the wettest places on Earth, receiving between 2 and 4 meters of rain per year, and the dense rainforest that covers most of the basin returns enormous quantities of this moisture back to the atmosphere through transpiration, creating a self-sustaining precipitation cycle that scientists call the flying rivers of the Amazon. The Amazon's flying rivers are among the more astonishing discoveries of modern hydrology. Researchers studying moisture transport over South America found that the Amazon rainforest does not simply receive rain, it actively generates it. The forest transpires so much water vapor from its leaf surfaces that it creates atmospheric rivers of water-laden air that flow westward and southward, driven by the rotation of the Earth and the geography of the Andes. These atmospheric moisture flows deliver rainfall to agricultural regions of southern Brazil, Bolivia, Paraguay, and Argentina that would otherwise be far too dry to sustain their current productivity. Studies published in the early 2010s suggested that the water falling on the farms of Mato Grosso, one of Brazil's most productive agricultural states, had, just weeks earlier, been transpired by trees in the central Amazon. This finding transformed the conservation debate in Brazil. Cutting the Amazon was no longer only a question of biodiversity or carbon storage. It was a question of whether the agricultural economy of an entire subcontinent could continue to function without the atmospheric services provided by a forest that took millions of years to assemble. The Amazon is also a river of extraordinary biological richness, harboring species whose very existence seems to violate assumptions about what freshwater ecosystems can contain. The Amazon river dolphin, known locally as the boto or pink river dolphin, is the largest freshwater cetacean on Earth. Unlike its marine cousins, it has evolved a flexible neck capable of turning its head 90 degrees, an adaptation to the flooded forest environment, where navigating around submerged tree trunks requires a maneuverability that oceanic dolphins never need. Its echolocation system is among the most sophisticated of any freshwater species, capable of detecting fish hidden beneath layers of leaf litter on the forest floor when the river floods during the wet season. The boto's pink coloration, more pronounced in older males, arises from blood vessels close to the surface of its nearly translucent skin. In Amazonian indigenous mythology, the boto is a shapeshifter, a seducer who emerges from the river at night in human form. This mythology has historically provided the animal with a degree of cultural protection, making taboo any attempt to hunt or harm it. The flooded forests of the Amazon, called várzea when seasonally inundated by whitewater rivers and agapo when flooded by blackwater rivers, represent one of the most unusual aquatic habitats on the planet. During the wet season, the Amazon and its tributaries can rise by as much as 14 meters, spreading across the forest floor for distances of up to 50 kilometers from the main channel. Fish swim among the canopy, feeding on fruits and seeds that fall from the trees above. At least 200 species of Amazonian fish are known to be frugivores, fruit eaters, and their seed dispersal role in the flooded forest is so significant that the collapse of fish populations would alter the forest's regeneration patterns. The tambaqui, a large-bodied pacu related to the piranha, has evolved teeth so powerful that it can crack open the hard seeds of rubber trees floating at the water's surface. The relationship between this fish and the trees it feeds upon has co-evolved over millions of years, and the spatial distribution of certain tree species in the Amazon is, in part, a map of the historical feeding ranges of the fish that dispersed their seeds. Blackwater rivers, like the Rio Negro, the Amazon's largest tributary, derive their dark, tea-colored appearance not from sediment but from dissolved organic compounds called tannins and humic acids. These substances leach from decomposing leaf litter in the surrounding forest, staining the water a deep amber or coffee color. The result is a water chemistry radically different from the sediment-rich, white water of the main Amazon. Blackwater rivers are extremely acidic, often with a pH comparable to black coffee, and remarkably low in dissolved nutrients. Yet they support extraordinary fish diversity. The Rio Negro alone is home to over 700 species of fish, more than in all of Europe's rivers combined. A figure that challenges the assumption that nutrient-poor environments must be biologically impoverished. The secret appears to lie partly in the very antiquity of these systems. The Rio Negro's fish fauna has been diversifying in relative isolation for millions of years, exploiting highly specialized ecological niches that simply do not exist elsewhere. This biological richness, born of ancient isolation and chemical adversity, remains one of freshwater science's most celebrated paradoxes. The Congo River of Central Africa presents a mirror image of the Amazon in some respects, a vast tropical river draining an enormous rainforest basin, but it differs in one crucial way that makes it uniquely stabilizing in global terms. The Congo Basin straddles the equator, with roughly half its watershed in the northern hemisphere and half in the southern. Because the rainy seasons of the two hemispheres are offset by approximately 6 months, the Congo receives rainfall from one side of the equator or the other in almost continuous succession. The result is that the Congo River never has a truly dry season. Its discharge remains remarkably constant throughout the year, varying by a factor of only about 2 between minimum and maximum flow, far less variable than most rivers of comparable size. This stability makes the Congo, along with the Amazon, one of the 2 rivers that together sustain the world's 2 largest intact tropical rainforests. Its depth, over 200 meters in places, means distinct fish populations have evolved in the lightless channel, isolated from surface relatives by conditions as extreme as separate floors of the ocean. Deep within the Congo's lightless underwater canyons, scientists have documented one of the most remarkable examples of parallel evolution in freshwater biology. At least 2 species of blind, depigmented fish belonging to the genus Teleogramma have independently lost both their eyes and their skin pigmentation while colonizing the extreme depths of the river's fast-flowing gorges. More extraordinary still, researchers studying the genetics of fish populations in the Congo's deep gorge found that surface-dwelling and deep-dwelling forms of the same species were diverging at the genetic level despite living in the same river, separated not by mountains or deserts, as one might expect from geographically isolated populations, but by depth and current speed alone. This process, called ecological speciation, suggests that the Congo's unusual combination of extraordinary depth and powerful currents has created invisible barriers within the river itself, parceling the aquatic world into ecological islands as effectively as any stretch of dry land. It is evolution happening not across millions of years but, in geological terms, in the very recent past. A reminder that rivers are not merely conduits of water but generators of biological novelty. The geological force most responsible for shaping individual river courses is erosion, but erosion is far from a simple or uniform process. Rivers erode their beds and banks through several distinct mechanisms. Hydraulic action occurs when the sheer force of moving water pries loose particles from the bed. Abrasion happens when transported sediment acts like sandpaper, grinding down the surfaces it contacts. Solution erosion or corrosion occurs in rivers flowing over soluble rock like limestone, where the slightly acidic water dissolves the rock chemically over time. And cavitation, the most violent of all erosion mechanisms, occurs in extreme rapids when the water moves so fast that pressure differences create microscopic bubbles that collapse with explosive force against the riverbed. This last mechanism was long thought to be confined to engineered hydraulic systems, but there is growing evidence that it operates in the world's most powerful natural waterfalls and cataracts. The erosive power of rivers is ultimately what renders all mountains temporary. Without rivers to carry eroded material to the sea, the continents would pile higher and higher with their own debris. Rivers are the planet's great levelers, and their work is never done. The relationship between a river and the bedrock it flows across produces some of the most dramatic landforms on Earth. When a river crosses alternating bands of hard and soft rock, differential erosion creates a landscape of rapids and gorges, with the hard rock standing proud as waterfalls and the soft rock worn away into deep plunge pools below. Niagara Falls, on the border between New York State and Ontario, is a textbook example of this process in action. The falls are maintained by a cap of hard Lockport dolomite underlain by softer shales and sandstones. As water plunges over the brink, it erodes the softer layers beneath the cap, eventually undermining it and causing chunks of the hard upper layer to break free and tumble into the gorge. This process causes Niagara Falls to retreat upstream at a rate that has averaged roughly 1 meter per year over the past 12,000 years since the end of the last ice age. The entire 7-kilometer gorge below the current falls is thus a record of the fall's retreat, a canyon carved not slowly by millions of years of gentle erosion but dynamically, in a geological eye blink, since the glaciers retreated. Not all erosion is linear or straightforward. Rivers that carry very high sediment loads relative to their water discharge, a condition that often arises when flows decrease or when the land they drain delivers excessive material, do something counterintuitive. They deposit sediment instead of eroding it, raising their own beds progressively above the surrounding land. These rivers, called aggrading rivers, are among the most hazardous systems in fluvial geomorphology. The classic aggrading river is one that has been forced to slow down, either by a gentler gradient as it approaches a coast, or by a decrease in discharge caused by human water extraction. As the bed rises, the water periodically overflows the banks and spreads across the floodplain, depositing levees of coarse sediment along the channel margins. Over time, these natural levees raise the channel higher and higher, creating a situation geomorphologists describe as a perched or hanging river. The Yellow River in its lower reaches is the most extreme example on Earth, where the riverbed stands more than 10 meters above the surrounding floodplain in some sections, a hydrological sword of Damocles suspended over one of the most densely populated regions of China. Meandering rivers are among the most beautiful and geometrically elegant phenomena in all of physical geography. When a river flows across a flat, alluvial plain with a gentle gradient and a moderate sediment load, it almost inevitably develops a sinuous, snake-like course. The reasons are rooted in fluid dynamics. Even the slightest irregularity in a straight channel creates a helical flow pattern called secondary circulation, which progressively erodes the outer bank of any curve while depositing sediment on the inner bank. The curve amplifies itself over time, growing tighter and more pronounced until the river is looping back and forth across its floodplain in sweeping arcs. The mathematical ratio that characterizes meandering channels, the sinuosity ratio, which compares actual channel length to straight line distance, is often between 1.5 and 4, meaning a river may travel 3 or 4 kilometers to cover 1 kilometer in a straight line. This self-organizing geometry, identical in its mathematics from a small meadow stream to the lower Mississippi, is one of the most arresting demonstrations of physical law operating silently across scales. The geometry of meanders is governed by a relationship of remarkable consistency across rivers of vastly different sizes. The radius of curvature of a meander bend, the size of the arc the river traces, tends to be proportional to the channel width, typically falling between 2 and 3 times the width of the channel. This means that the Mississippi River, with a channel width of perhaps 800 meters in its lower reaches, develops meanders with radii of curvature around 2 kilometers, while a small meadow creek a meter wide develops meanders with radii of just a few meters. The underlying physics is the same at both scales. More intriguingly, meander geometry has been found not only in rivers but in glacial meltwater streams flowing under ice sheets, in tidal channels on salt marshes, and even in streams on other planets. Images from NASA's Mars Reconnaissance Orbiter have revealed sinuous channels on the Martian surface with meander geometries consistent with rivers of flowing water, providing some of the strongest evidence that liquid water once moved across the Martian landscape in a geologically coherent and sustained fashion. When a meander grows so extreme that the river's looping course nearly doubles back on itself, a dramatic and often sudden event occurs. During a flood, the river may break through the narrow neck of land separating 2 adjacent loops, abandoning the long curved channel and taking a shortcut across the neck. The abandoned loop, cut off from the main channel, becomes an oxbow lake, a crescent-shaped body of still water lying alongside the new, straighter course. Oxbow lakes are common features of large river floodplains worldwide, and they play important ecological roles as nurseries for fish, refugia for waterfowl, and indicators of a river's historical course. The Mississippi River floodplain contains hundreds of oxbow lakes, relict meanders of various ages that record the river's wandering history across its alluvial valley like a sprawling abstract painting. Some of these features formed within historical memory, others are thousands of years old. By mapping their positions and estimating their ages using radiocarbon dating of organic sediments, geomorphologists can reconstruct how the Mississippi's course has migrated laterally across its floodplain, sometimes shifting by tens of kilometers within a few centuries. The Mesopotamian civilizations, literally meaning land between the rivers, in ancient Greek, from the Tigris and Euphrates, represent perhaps the most complete historical case study of how river geography shapes the rise and fall of complex societies. The 2 rivers, both originating in the mountains of eastern Anatolia, descend through what is now Turkey, Syria, and Iraq, converging in the marshes of southern Iraq before emptying into the Persian Gulf. Between them, they created the first agricultural revolution in human history around 10,000 years ago, when early farmers in the Fertile Crescent discovered that the annual floods depositing rich silt on the floodplains made cultivation possible in a region that would otherwise be too dry to farm. But the rivers were less predictable than the Nile, and their floods were often violent and destructive rather than gentle and enriching. The unpredictable floods of Mesopotamia may help explain why the flood myths of ancient Sumerian and Babylonian literature, most famously in the Epic of Gilgamesh, portray inundation not as divine blessing but as divine wrath, an existential terror to be survived rather than a seasonal gift to be welcomed. The ancient irrigation systems of Mesopotamia were engineering achievements of startling ambition. The water of the Tigris and Euphrates flows above the level of the floodplain in the upper reaches of the alluvial plain, a natural geometry that the Sumerians exploited by cutting channels diagonally across the plain to carry water by gravity to fields that would otherwise be unreachable. These early canals, some documented as early as 4000 BCE, required coordinated labor at a scale that historians believe drove the development of early state bureaucracy. Someone had to organize the digging, maintain the channels against siltation, and regulate the distribution of water during dry seasons. The Code of Hammurabi, the Babylonian legal text from approximately 1754 BCE, contains specific provisions governing the maintenance and use of irrigation canals, making water law one of the oldest bodies of codified human regulation in existence. The collapse of these irrigation systems, accelerated by salinization of soils caused by centuries of waterlogging, is now understood to be one of the primary factors in the decline of ancient Sumerian city-states, a slow agricultural poisoning written in the chemistry of river water applied to vulnerable land. The Indus Valley Civilization, which flourished between approximately 3300 and 1300 BCE in what is now Pakistan and northwestern India, built its cities along the banks and floodplain of the Indus River system with a spatial precision and urban planning sophistication that rival anything the ancient world produced. Cities like Mohenjo-daro and Harappa were laid out on grid plans with standardized brick sizes, sophisticated covered drainage systems, and what appear to be municipal water storage facilities, all in a civilization that predated ancient Greece by more than 2,000 years. The Indus civilization's urban water management suggests an advanced understanding of hydrology and public health that was not rediscovered in the Western world until the Roman Empire, and arguably not matched until the 19th century. Yet this civilization, so dependent on the seasonal flooding of the Indus and its tributaries to sustain its agriculture, appears to have been undone in part by a massive hydrological disruption, the drying up or course change of a major river, possibly the mythical Sarasvati described in ancient Vedic texts, which may have been the Gagarhakra river system, now largely dry, that once ran parallel to the Indus. River capture, also called stream piracy, is a geological process in which one river system gradually erodes its way into the watershed of a neighboring river and steals its headwaters, dramatically altering the drainage patterns of a region. The mechanism is straightforward. A stream that is eroding headward more vigorously, perhaps because it has a steeper gradient or is flowing over softer rock, may eventually break through the divide separating it from an adjacent watershed. When breakthrough occurs, the beheaded river suddenly loses much of its discharge, shriveling into a misfit stream, a wide valley occupied by a tiny trickle that seems absurdly undersized for the landform containing it. Evidence of ancient river captures is preserved across many landscapes in the form of these wind gaps and misfit streams, silent testimony to drainage reorganizations that occurred millions of years ago. The current drainage of the eastern United States, for instance, bears the marks of multiple ancient captures that redirected major river systems from westward draining patterns into their present eastward flowing configurations as the Appalachian Mountains were eroded and their drainage basins reorganized over hundreds of millions of years. Some of the most dramatic river captures in geological history were not the result of gradual headward erosion but of catastrophic floods that reshaped drainage patterns in days or weeks rather than millennia. These glacial outburst floods, known by the Icelandic term jökulhlaups, occur when meltwater dammed behind glacial ice accumulates to critical pressure and suddenly releases, sending walls of water across the landscape with a violence that dwarfs anything seen in normal river floods. During the last ice age, the repeated catastrophic draining of glacial Lake Missoula, an ice-dammed lake in Montana that held roughly the volume of Lake Erie and Lake Ontario combined, sent floodwaters roaring across what is now eastern Washington state, carving the channeled scablands in a geological instant. The geologist J. Harlan Bretz proposed this hypothesis in the 1920s and was initially ridiculed by colleagues who could not accept that such catastrophic processes were geologically credible. Decades later, as evidence accumulated from aerial photography and field mapping, the scientific consensus shifted entirely. Bretz received the Penrose Medal, geology's highest honor, at the age of 96, a vindication as slow as erosion itself. The Colorado River is one of the most studied and most litigated rivers on Earth, and its story encapsulates almost every tension in modern water management. Originating in the Rocky Mountains of Colorado and Wyoming, it drains a watershed of nearly 630,000 square kilometers across 7 American states and 2 Mexican states before reaching the Gulf of California, or rather, before it used to reach the Gulf of California. Today, so much water is extracted from the Colorado by agriculture, cities, and industry that the river regularly fails to complete its journey to the sea. In most years, the Colorado simply disappears into the dry sand of the Sonoran Desert before crossing the border. This is not a natural condition. Before the construction of Hoover Dam in 1936 and the subsequent plumbing of the American Southwest, the Colorado carried an average annual discharge into the Gulf of California sufficient to maintain a rich delta ecosystem. That delta, once covering nearly 8,000 square kilometers of wetlands and estuaries, has been reduced to a fraction of its former extent, and the species that depended on it have been pushed toward extinction. Hoover Dam, completed in 1936, was at the time of its construction the largest concrete structure ever built and the most powerful hydroelectric facility in the world. Its construction required diverting the entire Colorado River through 4 massive tunnels bored into the canyon walls of Black Canyon, an engineering task that took nearly 3,000 workers 2 years to accomplish. The dam created Lake Mead, which at full capacity holds approximately 36 cubic kilometers of water, more than the combined annual flow of the Colorado River. For several decades, Hoover Dam represented the pinnacle of what engineering ambition and political will could achieve with a river. But its legacy is complicated. The reservoir traps virtually all of the Colorado's sediment, which previously nourished the delta and replenished the beaches of the lower canyon. Downstream of the dam, the sediment-starved water, clear and cold, began eroding the riverbed rather than depositing on it, incising a deeper and deeper channel through the canyon and removing the sandbars that had previously provided habitat for native fish and nesting sites for migratory birds. Hoover Dam solved one set of problems and created an entirely new set. The ecological consequences of large dams have transformed the scientific consensus about their desirability over the past 50 years. The fish species most catastrophically affected by dam construction are migratory anadromous fish, species that are born in freshwater rivers, migrate to the ocean to grow, and then return to their natal streams to spawn and die. Salmon are the most iconic of these, and their decline across dammed rivers in the Pacific Northwest of North America has been one of the most visible environmental stories of the 20th century. A salmon's ability to locate its birth stream after years at sea is one of the great navigation mysteries of biology. Research has confirmed that salmon use a combination of olfactory memory. They imprint on the specific chemical signature of their home stream as juveniles, and sensitivity to the Earth's magnetic field to guide their oceanic migrations. When they encounter a dam, however, no amount of navigational sophistication helps. The upstream migration is simply blocked. Fish ladders have been constructed at many dams to provide passage, but their effectiveness for large adult salmon navigating strong currents remains a subject of continuing debate among fisheries scientists. The science of fish passage at dams opened a broader field of inquiry into how rivers function as connected systems, where blockages at any point have consequences that ripple both upstream and downstream. Marine-derived nutrients delivered by spawning salmon. The carcasses of fish that die after spawning release nitrogen, phosphorus, and marine carbon into freshwater ecosystems, support not just the rivers themselves but entire terrestrial food webs. In the forests of Alaska and British Columbia, grizzly bears carry salmon carcasses away from streams and consume them in the woods, effectively fertilizing the surrounding trees with marine nutrients. Researchers have detected marine-derived nitrogen in the growth rings of trees growing hundreds of meters from salmon streams. When salmon runs collapse due to dam construction, the ripple effect moves outward. Bears are less well-fed, tree growth slows, the forest canopy changes, and the insect communities that depend on salmon carcasses as larval habitat decline. The dam does not simply block a fish. It disconnects a web of ecological relationships that evolved over millions of years and that now cannot function without its keystone species. The concept of river connectivity, The idea that rivers function as integrated systems linking headwaters to estuaries, channels to floodplains, and surface water to groundwater has emerged as central to modern freshwater conservation science. A river's health cannot be assessed by examining the channel alone. The hyporheic zone, the region beneath and alongside a river where surface water and groundwater mix, is now recognized as a distinct and critically important ecosystem. Water moving through the hyporheic zone follows complex three-dimensional paths, driven by pressure differences created by the irregular bed topography above. As it percolates through gravels and sands, it is filtered, cooled, and chemically transformed by microbial communities that oxidize organic compounds and cycle nutrients. Spawning salmon rely on cold, oxygenated hyporheic flows to keep their eggs viable through weeks of incubation. But when river channels are artificially straightened and lined with concrete, a practice common in agricultural and urban river management, the hyporheic zone is eliminated along with the microbial processing, thermal buffering, and spawning habitat it provides. The channel may still carry water, but it has been transformed from a living system into a pipe. Groundwater and rivers maintain a relationship more intimate than most people realize. In many landscapes, rivers are not simply carriers of surface runoff but expressions of the water table, the upper surface of the saturated zone in the soil and rock below. A gaining river receives water from the surrounding groundwater, and its discharge increases in the downstream direction even on days when no rain is falling. A losing river, by contrast, recharges the groundwater below it, its water seeping downward through a permeable bed and disappearing into the subsurface. Many rivers are gaining in some reaches and losing in others, depending on the local relationship between the water table elevation and the river stage. In arid regions, losing rivers can disappear entirely, their flow consumed by groundwater recharge before they reach any sea. The rivers of the Tarim Basin in China's Xinjiang region, fed by snowmelt from the Tian Shan and Kunlun ranges, lose their discharge progressively to the desert sands, maintaining a narrow thread of riparian habitat, tamarisk groves, reed beds, and Euphrates poplar forests, against the encroaching dune fields of the Taklamakan Desert. The rivers of the Himalayan system, the Indus, the Ganges, the Brahmaputra, the Mekong, the Yangtze, the Yellow River, and others, originate in the world's highest mountain range and collectively provide water to approximately 1.9 billion people, nearly a quarter of humanity. Their flows are sustained in part by seasonal monsoon rains, but also significantly by glaciers, vast frozen reservoirs of water that release meltwater through the summer months, sustaining river flows even during dry periods when precipitation has ceased. This glacial buffering effect makes the timing of river flows across South and Southeast Asia remarkably stable, anchoring the agricultural calendars of civilizations that have farmed these floodplains for thousands of years. Climate change, however, is now accelerating the melting of Himalayan glaciers at rates that concern hydrologists deeply. In the short term, accelerating melt may actually increase river flows, producing floods of unusual severity. But as glaciers shrink, the volume of summer meltwater they can release will decline, threatening the dry season flows on which hundreds of millions of farmers and city dwellers depend. Glaciologists describe the Himalayan glaciers as water towers, and water towers, once emptied, do not immediately refill. The Ganges River occupies a position in human culture and spiritual life that is without parallel among the world's rivers. Hinduism, practiced by over 1 billion people, holds the Ganga, as it is known in Sanskrit, to be a living goddess and the most sacred of all waters. Pilgrims travel hundreds or thousands of kilometers to bathe in its waters at the city of Varanasi, one of the oldest continuously inhabited cities on Earth, where the river's ghats, broad stone stairways descending to the water, receive hundreds of thousands of worshippers during major festivals. The scientific dimensions of the Ganges are no less extraordinary than the religious ones. Early colonial-era administrators and Indian traditional healers both noted that Ganges water appeared remarkably resistant to decomposition. Bodies of cholera victims could be submerged in the river without apparent spread of the disease downstream, an observation so counterintuitive that it generated scientific investigations spanning more than a century. The river thus served simultaneously as a water supply, a spiritual axis, and the most ancient form of climate monitor, its floods and droughts encoding the fate of entire empires. The Brahmaputra River, known in Tibet as the Yarlung Tsongpa, completes one of the most extraordinary geographical journeys of any river on Earth before it descends from the Tibetan Plateau. For most of its upper course, the Yarlung Tsongpa flows eastward across the high plateau at an elevation of over 4,000 meters, running in the opposite direction from what one might expect given that the ocean lies to the south. Then, near the eastern edge of the Himalayas, it encounters the Great Massif of Namcha Barwa, a peak rising to over 7,000 meters, and makes an abrupt U-turn, curving through one of the deepest gorges on the planet, the Yarlung Tsongpa Grand Canyon, at some sections more than 5 kilometers deep, and descending precipitously to the plains of Assam in northeastern India as the Brahmaputra. The river drops approximately 2,000 meters in elevation within this gorge, a descent so steep and so voluminous that it contains theoretical hydroelectric potential estimated at 100 gigawatts, more than the entire installed hydroelectric capacity of any single nation on Earth. China's plans to dam the lower gorge have generated significant geopolitical tension with downstream India. The Congo River flows through the heart of the African continent with a characteristic that sets it apart from almost every other major river on Earth. It never truly slows down. Even in its lower reaches, far from any mountains, the Congo maintains a powerful current driven not by elevation gain but by the enormous volume of water it must channel through a relatively narrow outlet. Where most major rivers broaden gradually as they approach their mouths, the Congo is constricted by a narrow gorge called Livingstone Falls, a series of rapids and cataracts near the river's mouth, which forces the enormous discharge through a passage barely a kilometer wide in places. The hydraulic pressure this creates generates the extraordinary depths already noted. But the gorge also creates something else, standing waves and hydraulic jumps of a size rarely seen in natural rivers, where the water piles up against itself and rebounds in walls of whitewater several meters high. These permanent hydraulic features have been studied by engineers designing turbines, because the Congo's lower gorge holds more developable hydroelectric potential than almost any other site on the planet. The Grand Inga site on the Congo River has tantalized energy planners for decades. Two existing smaller dams at Inga already generate more than 1,700 megawatts of power. The proposed Grand Inga Dam, if ever built to its full design capacity, would generate approximately 44,000 megawatts, making it by far the largest power station in human history, capable of doubling the electricity supply of the entire African continent. The project has been discussed, planned, and repeatedly deferred since the 1970s. The costs are staggering. Estimates range between $80 and $100 billion, and the environmental and social impacts would be substantial. A reservoir of this scale in the lower Congo Gorge would flood significant areas of rainforest and displace tens of thousands of people. The electricity, moreover, would need to be transmitted across thousands of kilometers of underdeveloped grid infrastructure to reach the majority of Africans who lack access to electricity. Critics argue that distributed small-scale solar and hydropower installations could deliver power to more people, more quickly, at lower cost and with less ecological disruption. The Grand Inga debate is, in microcosm, the entire debate about large-scale hydropower in the 21st century. Hydroelectric power occupies a complex position in contemporary energy policy. On one hand, it is genuinely renewable, driven by the solar-powered water cycle, and produces no greenhouse gas emissions during operation. On the other hand, reservoirs created by large dams emit methane and carbon dioxide as submerged organic matter decomposes in the anaerobic conditions at the bottom of deep impoundments. In tropical regions, where plant biomass is dense and water temperatures are warm, this reservoir emission can be substantial enough to make some large tropical dams nearly as carbon-intensive as natural gas power plants over their operational lifetimes. The Balbina Dam in the Brazilian Amazon, which flooded over 2,000 square kilometers of rainforest in 1989, became notorious as a case study in this phenomenon. Its relatively small power output, it generates only around 250 megawatts, is generated at carbon cost of exceptional irresponsibility. Researchers continue to refine life cycle emissions calculations for hydroelectric projects, seeking more defensible assessments of when tropical hydropower is genuinely beneficial and when its carbon debt outweighs its renewable credentials. Run-of-river hydroelectric projects represent an alternative paradigm, one that harnesses the kinetic energy of flowing water without creating large reservoirs. Instead of damming a river to create a head of water, run-of-river installations divert a portion of the river's flow through a canal or penstock and pass it through turbines before returning it to the river downstream. The energy output of such projects is directly proportional to the natural flow of the river, which means generation varies with the seasons and cannot easily be dispatched on demand in the way that reservoir-based plants can. But the absence of a reservoir eliminates the most destructive ecological impacts of conventional hydropower: the inundation of forests and farmland, the blocking of fish migration, the trapping of sediment, and the disruption of temperature regimes downstream. Norway, which generates nearly all of its electricity from hydropower, has increasingly shifted toward run-of-river development in its remaining undeveloped river systems, viewing it as a more sustainable alternative that can expand renewable energy capacity without repeating the ecological mistakes of the large reservoir era. The trade-off between dispatchability and sustainability is one the energy sector is only beginning to navigate honestly. The Mekong River is one of the world's great rivers in almost every measure, the 12th longest globally, the 8th largest by discharge, and the most biodiverse freshwater system outside of the Amazon and Congo basins. It flows from the Tibetan Plateau through the Chinese province of Yunnan, then along the borders of Myanmar, Laos, and Thailand before entering Cambodia and Vietnam and emptying into the South China Sea through a vast delta of 9 distributaries. The Mekong's ecology is dominated by one extraordinary annual event: the reversal of the Tunnel Sap, a large lake in central Cambodia connected to the Mekong by a short tributary. During the monsoon season, the Mekong's swollen waters push back up the Tunnel Sap River, forcing the lake to expand from its dry season extent of about 2,500 square kilometers to a wet season area of up to 16,000 square kilometers. This reversal creates one of the world's most productive fisheries. The flooding exposes vast areas of forest floor as nursery habitat for juvenile fish, supporting the food security of millions of Cambodians for whom freshwater fish is the primary protein source. The Mekong fishery is not only extraordinary in scale but in biological composition. The river is home to the giant Mekong catfish, considered by many scientists to be the world's largest freshwater fish. Individuals reaching over 2 meters in length and weighing over 300 kilograms have been documented, though such giants are now extremely rare due to overfishing and habitat loss. The Mekong also hosts a remarkable diversity of large-bodied carp species, several species of freshwater stingrays including Himantura polylepis, documented at over 600 kilograms, and numerous endemic species found nowhere else on Earth. The construction of mainstream dams on the Mekong, particularly in the Chinese province of Yunnan, and a growing number of dams on the lower Mekong commissioned by Laos and Cambodia, have begun to alter the river's flood pulse in ways that threaten the Tunnel Sap's productivity. Satellite measurements have confirmed that the amplitude of the Tunnel Sap's annual expansion and contraction has decreased since upstream dams came online, reducing the inundation area available as fish nursery habitat. The social implications for Cambodia, a nation where freshwater fish accounts for roughly 70% of dietary protein, are potentially catastrophic. Fluvial geomorphology recognizes a concept known as the braided river, a theoretical state in which a river has achieved a dynamic equilibrium between the energy available to it from slope and discharge and the energy required to transport its sediment load. A braided river neither erodes its bed nor deposits sediment over the long term. It simply transports everything that enters it. This concept, formalized by the American geologist John Hoover Mackin in 1948, was enormously influential in shaping how geomorphologists understood river systems. But the braided river is ultimately an abstraction. Real rivers are never perfectly in equilibrium. They are always responding to disturbances, floods that exceed their capacity, droughts that strand sediment in the channel, earthquakes that shift the land surface, sea level changes that alter the base level toward which rivers adjust. The beauty of the graded river concept is not that it describes reality accurately, but that it provides a reference condition against which to measure the direction and magnitude of change. Understanding whether a river is a grading, degrading, or approximately stable is the first step in diagnosing its condition and predicting its response to any intervention. Rivers flowing over limestone bedrock produce landscapes of haunting beauty and geological intricacy. Limestone is soluble in slightly acidic rainwater, water that has absorbed carbon dioxide from the atmosphere or from soil to form weak carbonic acid, and its dissolution over millions of years creates karst topography, a distinctive landscape of sinkholes, caves, disappearing rivers, and springs that emerge without obvious surface catchments. In karst terrain, rivers often vanish abruptly into swallow holes in the riverbed, flowing through subterranean cave systems for kilometers before re-emerging at springs far downstream. The Reka River of Slovenia disappears underground at Scotchen Caves, flowing through a cavern system so large that its main hall has been described as one of the largest underground spaces in the world accessible to the public. The Trebišnjica River in Bosnia and Herzegovina was historically described as the longest sinking river in Europe, losing much of its discharge to the limestone beneath it. Rivers that flow through karst systems carry chemical signatures that allow hydrologists to trace their underground pathways using injected dyes or naturally occurring isotopes, mapping subterranean drainage networks invisible at the surface. Underground rivers in karst systems have fascinated explorers and scientists for centuries, and they present some of the most extreme environments inhabited by freshwater life. Species adapted to life in caves, collectively called stygobionts, typically display the same convergent features regardless of which continent or river system they inhabit: loss of eyes, loss of pigmentation, elongated sensory appendages, dramatically slowed metabolism, and lifespans far longer than their surface relatives. The olm, Proteus anguinus, a cave-dwelling salamander found in the underground rivers of the Dinaric Alps in Slovenia and Croatia, is a particularly remarkable stygobiont. Completely blind and depigmented, it can survive without food for up to a decade by reducing its metabolic rate to a fraction of a normal salamander's baseline. Remarkably, it is the longest-lived amphibian known to science, with estimated maximum lifespans exceeding 100 years. The olm's metabolism is so slow that it reproduces only once every 12.5 years on average. In the absolute darkness of its cave river environment, where resources are scarce but predators are absent and environmental stability is near perfect, evolution has produced an organism that seems almost to defy the conventional biological rules about the pace of life. The glacially carved lakes of the Alps and the Scottish Highlands contain rivers that are, in a strict technical sense, among the youngest on Earth. When the great ice sheets of the last glacial maximum retreated 12 to 14,000 years ago, they left behind a transformed landscape. New valleys, new coastlines, and countless new lakes formed in basins scoured by glacial erosion. The rivers that drain these lakes began flowing only after the ice retreated, and in many cases their current courses follow glacially modified valleys that bear no relationship to the pre-glacial drainage. Loch Ness in Scotland, famous for its improbable resident, is drained by the River Ness flowing to the Moray Firth, but the loch itself is part of the Great Glen Fault, a major tectonic lineament, and the valley it occupies was shaped by the intersection of tectonic and glacial processes over timescales far longer than the river's current course. Rivers in post-glacial landscapes are often described as misfit streams, occupying valleys far too large for their current discharge, because the valleys were carved by glacial meltwater torrents vastly more powerful than any modern river flowing in them. Braided rivers are among the most dynamic and visually distinctive of all river forms. Unlike the single-thread meandering channels that typify lowland rivers in temperate regions, braided rivers divide into multiple interlocking channels separated by transient islands and bars of gravel and sand. The braiding pattern arises when a river's sediment load exceeds its transport capacity. When the river carries more material than it can move, it begins depositing mid-channel bars that force the water to divide around them. Braided rivers are characteristic of proglacial environments, the outwash plains beyond glaciers, where streams loaded with glacially comminuted sediment are constantly depositing excess material. They are also found downstream of active volcanic systems, where lahars and ash flows provide extraordinary quantities of new sediment. The Canterbury Plains of New Zealand's South Island are crossed by numerous large braided rivers, the Waimakariri, the Rakaya, the Rangitata, that carry gravel from the southern Alps across the plains to the Pacific. These rivers are considered among the finest examples of actively braided systems in the world, and they are studied intensively by geomorphologists seeking to understand the physics of sediment transport under conditions of chronic oversupply. The physics of sediment transport reaches its most spectacular expression in turbidity currents, underwater avalanches of sediment-laden water that roar down the continental slope and across the deep ocean floor. These phenomena, though invisible at the surface, are among the most powerful erosional agents on the planet. When a river deposits enormous quantities of sediment at the continental shelf edge, the accumulated material can become unstable and collapse, transforming into a dense flow of water and sediment that surges down submarine canyon systems at speeds of up to 80 kilometers per hour. Turbidity currents can travel thousands of kilometers across the flat abyssal plains, depositing their sediment loads in graded layers called turbidites that accumulate over geological time into thick sequences of deep-sea sediment. The mechanism was first proposed by the American geologist Philip Quenin in 1950, and the hypothesis received dramatic confirmation from the records of transatlantic telegraph cables broken in sequence during the 1929 Grand Banks earthquake. The pattern of cable breaks revealed a turbidity current moving at speeds consistent with Quenin's predictions, a geological process detected inadvertently by its destruction of technology built to connect continents. River deltas, the landforms built at the mouths of rivers where their sediment meets the standing water of a sea or lake, are among the most productive and most threatened landscapes on Earth. A delta forms when a river's velocity suddenly drops as it enters standing water, causing it to deposit its sediment load. Over time, this deposition builds the land seaward, creating a mosaic of distributary channels, wetlands, mangrove forests, and mudflats that support extraordinary biological diversity and provide natural protection against storm surges. The Ganges-Brahmaputra Delta, the Sundarbans, is the world's largest delta and contains the largest remaining area of contiguous mangrove forest, a UNESCO World Heritage Site inhabited by the Royal Bengal tiger, the Irrawaddy dolphin, and hundreds of species of birds and reptiles. The Nile Delta, the Mississippi Delta, the Yangtze Delta, and the Mekong Delta support some of the densest agricultural populations on Earth. But deltas worldwide are sinking, in many cases literally disappearing beneath rising seas. Deltas worldwide are now sinking and retreating simultaneously, victims of sediment starvation from upstream dams, groundwater extraction causing subsidence, and the accelerating sea level rise of a warming climate. The Mississippi River Delta is currently losing approximately a football field of land to the sea every hour and a half, a rate of coastal erosion so alarming that it has transformed Louisiana coastal politics and become a symbol of the broader crisis facing river deltas globally. The root cause is complex. The Mississippi delivers far less sediment to its delta today than it did before the 20th century, because sediment that was once carried to the coast is now trapped behind the more than 20,000 dams and weirs in the Mississippi-Missouri River system. Simultaneously, the extensive levee system built after catastrophic floods, culminating in the Mississippi River and Tributaries Project initiated after the 1927 flood, prevents the river from spreading across its floodplain during high water events, eliminating the overbank deposition that historically built the delta's sediments. Without fresh sediment input, the delta compacts and subsides under its own weight while the sea simultaneously advances. New Orleans, already sitting partly below sea level, is subsiding at rates of up to 2 centimeters per year in some neighborhoods. The Venetian Lagoon, connected to the Adriatic Sea by 3 inlets and fed by several small rivers draining the surrounding plain, presents a different kind of river-sea interaction story. Venice, built on a cluster of mudflat islands in this lagoon, is one of humanity's most audacious experiments in constructing civilization on ground made almost entirely of river-deposited sediment. The islands on which Venice stands are composed of alluvial material deposited by the rivers of northern Italy over millennia. The city itself began as a refuge, its inaccessibility via land protecting its founders from invaders during the chaos of the early medieval period. For centuries, the Venetians managed the lagoon's hydrology with extraordinary care, diverting several rivers that had previously emptied into the lagoon, including the Brenta, the Sile, and the Piave, to prevent siltation that would eventually convert the lagoon to dry land. This intervention was itself ecologically consequential, as it reduced the sediment supply that had historically compensated for natural subsidence, contributing to the very sinking problem that Mos, the city's recently activated movable barrier system, was designed to address. The Po River, flowing eastward across the plain of northern Italy to the Adriatic, is the longest river in Italy and carries sediment loads that have historically built the Adriatic coastline of the Po delta outward at rates of hundreds of meters per century. Where the Po meets the sea, the delta's productive wetlands and brackish lagoons support one of Europe's most important migratory bird staging areas and a traditional culture of fishing and eel harvesting that dates back to Roman times. Like so many river deltas, the Po delta is now retreating rather than advancing, the result of sediment trapping by upstream dams, large-scale extraction of methane gas and groundwater from beneath the plain, which causes subsidence, and the straightening and channeling of the river for flood control. Satellite measurements show that parts of the delta are sinking at rates of 2 to 3 centimeters per year. Its geochemical signature records the entire sweep of land use across the Po plain, each era's farming practices written in the river's dissolved mineral and nutrient loads for those who know how to read them. Rivers carry not only sediment and water but the entire chemical signature of their watersheds. The dissolved mineral content of river water, expressed as total dissolved solids or TDS, varies enormously depending on the geology through which the river passes. Rivers draining ancient metamorphic and igneous rocks, where minerals are largely insoluble, carry very little dissolved material and are described as soft water. Rivers draining sedimentary formations rich in evaporites, limestones, and gypsum carry high dissolved loads and produce hard water. The Amazon River, despite its enormous discharge, is remarkably soft. Its TDS is among the lowest of any major river, because the ancient, weathered rocks of the Guiana and Brazilian shields have been leached of their soluble minerals over hundreds of millions of years. The rivers of the Arabian Peninsula, in contrast, carry some of the highest dissolved solid concentrations of any freshwater system, because they drain evaporitic sediments and receive so little rainfall that salts concentrate rather than dilute. This chemical diversity of rivers has profound consequences for the life they support, the soils they irrigate, and the marine chemistry of the coastal seas they feed. One of the most important chemical roles that rivers play in the global Earth system is the delivery of nutrients to coastal marine environments. Rivers carry dissolved nitrogen, phosphorus, silica, and iron to the sea, where these elements stimulate the growth of marine phytoplankton. In coastal zones adjacent to large river mouths, phytoplankton blooms fueled by river nutrients support some of the most productive fisheries on the planet. The continental shelves near the Mississippi, the Congo, the Amazon, and the Yangtze mouths are among the most biologically rich marine environments in the world. But the same nutrient delivery that supports fisheries can, in excess, devastate coastal ecosystems through a process called eutrophication. When rivers carry excessive nitrogen from agricultural fertilizers and sewage, the resulting phytoplankton blooms are too abundant for the ecosystem to process. When the bloom dies and sinks, bacterial decomposition consumes all available dissolved oxygen, creating hypoxic, dead zones, where almost no multicellular marine life can survive. The Gulf of Mexico dead zone, fed each year by nutrient runoff from the entire Mississippi-Missouri agricultural basin, is one of the world's largest, covering at its maximum extent over 20,000 square kilometers of seafloor. The Colorado River's relationship with the Grand Canyon is one of the most powerful demonstrations of long-term erosive power in all of geology. The Colorado began cutting into the Colorado Plateau approximately 5 to 6 million years ago, when a combination of plateau uplift and the integration of the river's drainage to the Gulf of California provided the gradient necessary to begin deep incision. Over those millions of years, the river removed approximately 10 cubic kilometers of rock per thousand years, an impressive rate that nonetheless seems almost impossibly slow when you stand on the rim of the Grand Canyon and contemplate its 1.6-kilometer depth and 446-kilometer length. What makes the canyon so scientifically valuable is not merely its size but the stratigraphic record it exposes. The rock layers visible from the rim represent nearly 2 billion years of Earth history, roughly half the age of the planet, in a sequence so complete and so accessible that it transformed early geology. John Wesley Powell's 1869 expedition down the Colorado produced the first systematic geological description of the canyon, establishing the conceptual framework for understanding deep time across the American West. The age of the Grand Canyon has been the subject of surprising scientific controversy in recent years. The traditional view, based on the timing of the Colorado River's integration to the Gulf of California, held that most of the canyon's incision occurred within the last 5 to 6 million years. But a 2012 study published in the journal Science, using a technique based on the decay of uranium and thorium isotopes trapped in cave minerals within the canyon walls, suggested that at least part of the western Grand Canyon was already deeply incised some 70 million years ago, potentially making it a Mesozoic feature subsequently modified and extended by the younger Colorado River. The hypothesis remains controversial, with subsequent studies producing conflicting results and interpretations, and the debate has injected new energy into one of the most studied geological features in the world. It illustrates a broader truth about river science. Even the most exhaustively investigated rivers still hold their secrets. The Grand Canyon has been studied by thousands of geologists over more than a century and a half, and fundamental questions about its origin and evolution remain genuinely unsettled. The Yangtze River, Asia's longest at over 6,000 kilometers and the world's third longest, drains approximately 1/5 of China's land area and is central to the history, culture, and economy of one of the world's great civilizations. Its upper reaches, carving through the mountains of western China, contain the Three Parallel Rivers World Heritage Site, a section of Yunnan province where the Yangtze, the Mekong, and the Salween run within 80 kilometers of each other, separated by knife-edged ridges, before diverging to empty into 3 different seas thousands of kilometers apart. This geographical anomaly is the result of the collision between the Indian subcontinent and Asia that built the Himalayas and compressed the river systems of Southeast Asia into their current extraordinary configuration. The Three Parallel Rivers region is also one of the most biodiverse temperate areas on Earth, a biodiversity hotspot created by the convergence of 3 distinct ecological corridors and the extraordinary climatic diversity generated by the rapid elevation changes. Rivers in this region descend from alpine meadows at over 4,000 meters to tropical gorges below 1,000 meters within a horizontal distance of less than 100 kilometers. The Three Gorges Dam on the Yangtze River, completed in 2006, is the world's largest hydroelectric power station by installed capacity, generating approximately 22,500 megawatts and producing annually enough electricity to replace the burning of approximately 50 million tons of coal. The dam's reservoir, the Three Gorges Reservoir, stretches more than 600 kilometers upstream, inundating entire cities, archaeological sites of enormous historical significance, and landscapes that had been inhabited continuously for thousands of years. The project required the relocation of approximately 1.3 million people, the largest planned population displacement in human history for an infrastructure project, and permanently altered the Yangtze's sediment dynamics, ecology, and thermal regime. Scientific assessments of the dam's ecological impacts describe a cascade of consequences: the near extinction of the Yangtze finless porpoise, the functional extinction of the Baiji River dolphin declared in 2006, the collapse of migratory fish populations including several endemic carp species, and the erosion of the Yangtze Delta downstream as sediment is intercepted by the reservoir. The dam produces electricity on a scale no alternative technology currently matches, and has imposed ecological costs on a scale that no subsequent intervention can easily repair. The Baiji River dolphin, Lipotes vexillifer, holds the distinction of being almost certainly the first large vertebrate driven to extinction by human activity in the 21st century. A December 2006 expedition by Chinese and international scientists traveled the entire length of the Yangtze from Shanghai to Yichang, deploying visual observation and acoustic monitoring equipment across 3,400 kilometers of river and recorded 0 sightings. The conclusion, while cautiously phrased as functionally extinct, was understood by the scientific community as the effective end of a lineage that had lived in the Yangtze for approximately 20 million years, since the Miocene epoch. The baiji was one of only 5 surviving freshwater dolphin species in the world and was genetically unique enough to represent not just a species but an entire family, Lepodidae. Its extinction was attributable to multiple compounding threats: overfishing that depleted its prey base, bycatch in illegal electric fishing gear, propeller strikes from the thousands of shipping vessels that use the Yangtze, and the profound disruption of the river's ecology by the Three Gorges Dam. Its extinction was a warning that freshwater megafauna face an accelerating crisis that will only worsen as rivers continue to be modified beyond ecological recognition. The disappearance of the baiji was not an isolated event but part of a global pattern of freshwater megafauna decline that researchers have documented with increasing alarm. A 2019 study in the journal Science Advances analyzed global population trends for freshwater megafauna, fish, reptiles, and mammals larger than 30 kilograms that depend on freshwater, and found that populations had declined by an average of 88% since 1970. This rate of decline is roughly twice that seen for terrestrial megafauna and far exceeds rates documented for marine species. The causes are multiple and interacting: dams that block migration routes, water extraction that reduces flows, pollution that degrades habitat quality, overfishing, and invasive species. Freshwater environments, despite covering less than 1% of Earth's surface, host approximately 10% of all known animal species, an extraordinary concentration of biodiversity that is simultaneously the most biologically rich and the most threatened category of ecosystems on Earth. Rivers are, in the literal sense of the word, irreplaceable. Freshwater environments, despite covering less than 1% of Earth's surface, host approximately 10% of all known animal species, a concentration of biodiversity as extraordinary as it is imperiled. River restoration science has grown rapidly since the 1990s, developing from an ad hoc set of local practices into a systematic discipline with its own journals, professional organizations, and evidence-based methodologies. The fundamental principle of river restoration is to reconnect rivers with their natural processes, their floodplains, their hypereich zones, their riparian vegetation, their sediment supply chains, by removing or modifying the barriers and channelization that have disrupted these connections. Dam removal has emerged as one of the most powerful and dramatic restoration tools. Since the early 1990s, hundreds of dams in the United States have been removed, ranging from small mill dams a meter high to large structures like the Elwha Dam in Washington state, removed in 2012. The Elwha River restoration following that dam removal has been one of the most intensively monitored river recovery projects in history, and its results have been remarkable. Within years of removal, salmon populations began recolonizing the upper river, sediment began rebuilding the delta at the river's mouth in the Strait of Juan de Fuca, and riparian vegetation began establishing on the newly exposed floodplain. River vegetation, the riparian corridor of trees, shrubs, and grasses lining riverbanks, performs hydrological and ecological functions that are only now being fully appreciated. Riparian trees shade streams, maintaining cool temperatures critical for cold water fish like trout and salmon. Their roots bind the bank sediments, slowing erosion and filtering pollutants before they reach the channel. Fallen trees, large woody debris, create habitat complexity in the channel itself, providing hiding places for fish, substrate for invertebrate communities, and forming natural small dams that retain water and sediment during dry periods. In the Pacific Northwest of North America, old-growth forests adjacent to salmon streams produce logs of such size and quantity that the rivers flowing through them are partially transformed into logjam mazes of habitat complexity. The loss of old-growth forest from these watersheds over the past century has reduced the input of large wood to streams dramatically. Restoration projects that reintroduce large wood to previously cleared streams produce measurable improvements in fish habitat quality within years of intervention. It is one of the few river restoration techniques that can be implemented rapidly and inexpensively, yielding ecological returns that far exceed the investment. The role of beavers in shaping freshwater ecosystems deserves a place in any serious exploration of rivers. No other non-human organism modifies river channels as radically or as effectively as Castor canadensis in North America and castor fiber in Eurasia. A beaver dam on a small stream transforms a single-thread channel flowing quickly over a pebble bed into a complex of ponds, channels, and wetlands. The impounded water raises the water table in the surrounding landscape, sustains stream flows during dry seasons by storing water that drains slowly, and creates habitat for dozens of species. Analysis of historical surveys in North America suggests that beaver populations in the pre-colonial period sustained a network of ponds and wetlands so extensive that the continent's river systems functioned quite differently from how they do today. The extirpation of beavers through fur trapping between the 17th and 19th centuries caused a cascading simplification of freshwater habitats that preceded by centuries the industrial-era dam building ecologists now study. Reintroduction of beavers has since emerged as a cost-effective restoration tool in both Britain and the American West, delivering ecological returns that consistently exceed the modest investment required. The river systems of the African Great Lakes region present hydrological and biological puzzles on a scale unique in freshwater science. The lakes themselves, Victoria, Tanganyika, Malawi, Albert, Edward, and others, are not simply isolated water bodies but nodes in an ancient and evolving drainage network shaped by the ongoing tectonics of the East African Rift. Lake Tanganyika, the world's second oldest lake at approximately 9 to 12 million years, is so deep, 1,470 meters at its maximum, that its lower layers are permanently anoxic, separated from the oxygenated surface by a thermocline so stable that almost no mixing occurs. The biological diversity of the lake's shallow water zones is staggering. Approximately 250 species of cichlid fish, the vast majority found nowhere else in the world, have evolved within this single lake system. The rivers connecting the Great Lakes create pathways for biological dispersal and barriers to it in complex and shifting configurations as tectonic movements alter drainage patterns over geological time. Lake Victoria was once believed to have dried completely around 15,000 years ago, an event requiring total recolonization, explaining why its cichlid diversity, vast as it is, remains younger than Tanganyika's. The most remarkable story in lake evolution is also a cautionary tale in conservation biology: the introduction of the Nile perch, Lates niloticus, into Lake Victoria in the early 1950s triggered what has been described as the largest mass extinction of vertebrates in recorded history. The Nile perch, a large predatory fish capable of reaching nearly 2 meters in length and weighing over 200 kilograms, was introduced with the intention of creating a commercial fishery. It accomplished this goal spectacularly. Today, Nile perch supports a multi-billion-dollar export fishing industry. But at a cost. The lake's endemic haplochromine cichlids, a flock of approximately 500 unique species representing one of the greatest radiations of vertebrate evolution ever documented in a single water body, declined catastrophically as Nile perch predation drove perhaps 200 of them to extinction. The cichlids were not merely biological curiosities. They performed critical ecological functions within the lake, grazing algae, processing detritus, and sustaining the food web on which the lake's entire productivity ultimately depended. Their loss triggered algal blooms, oxygen depletion, and cascading ecological changes that now threaten the long-term viability of the very fishery their extinction helped to create. The Thames River in England carries within its mud an astonishing archive of human history. Over centuries, objects discarded, dropped, or deposited in the river by every wave of inhabitants have accumulated in the intertidal sediment of its banks, preserved by the cold, dark, low-oxygen conditions from rapid decay. The practice of mudlarking, searching Thames foreshore sediments for historical artifacts, has a history extending from the 18th century, when impoverished Londoners made their living salvaging coal and metal scraps from the riverbank, to the present day, where it constitutes a legally regulated form of amateur archaeology. Objects recovered from the Thames mud have included Roman coins, medieval pilgrim badges, Tudor shoes, post-medieval tobacco pipes, Victorian toys, and countless other fragments of ordinary and extraordinary life. But the Thames is not only an archaeological record, it is also a biological one. The river's recovery following construction of Bazalgette's sewage system was remarkable. Migratory Atlantic salmon returned to the Thames in 1974 for the first time in over a century, a biological verdict on what becomes possible when a civilization chooses to treat its rivers as something other than drains. The Rhine River, flowing from the Swiss Alps to the North Sea through some of the most industrialized terrain in Europe, has been one of the great case studies in both river pollution and river recovery. By the 1970s, the Rhine was widely described as the sewer of Europe. Industrial discharge from chemical factories in Switzerland, Germany, and the Netherlands had contaminated the river with heavy metals, chlorinated compounds, and organic pollutants at concentrations that rendered the river biologically dead in its middle reaches. The International Commission for the Protection of the Rhine, established in 1950, accelerated its work dramatically following the 1986 Sandoz chemical spill in Basel, when a warehouse fire caused approximately 30 tons of pesticides to enter the Rhine, killing approximately 500,000 fish over 480 kilometers of river and triggering a massive public and political response. The Rhine Action Program, launched the following year, set ambitious targets for reducing pollutant loads and restoring salmon populations. Today, returning salmon and vastly reduced contaminant levels in the Rhine demonstrate that major rivers can recover from extreme pollution if the political will exists to fund and enforce the necessary changes over decades. The physics of river flow at the point where it meets the sea produces one of the most complex and ecologically productive environments in the natural world, the estuary. An estuary is not simply the place where a river ends but a dynamic zone of mixing between freshwater and saltwater where salinity, temperature, turbidity, and current direction all vary on tidal, diurnal, and seasonal timescales simultaneously. The precise mixing patterns in an estuary are determined by the relative strengths of river inflow and tidal prism, the volume of water exchanged with the sea each tidal cycle. In estuaries where river inflow strongly dominates, the freshwater tends to ride over the saltwater in a distinct wedge, the two layers barely mixing. In estuaries where tidal energy dominates, intense mixing produces nearly uniform salinity throughout the water column. Most natural estuaries fall somewhere between these extremes, with the salinity and mixing pattern shifting seasonally as river discharge varies. This physical complexity generates extraordinary biological productivity. Estuaries are nursery habitats for the juveniles of many marine species, feeding grounds for migratory birds, and spawning areas for anadromous fish. The Mississippi River carries within its water column a chemical history of American agriculture over the past century and a half. Nitrate concentrations in the river have approximately doubled since the 1960s, driven by the expansion of synthetic nitrogen fertilizer use in the Corn Belt states of Iowa, Illinois, Minnesota, and others. This nitrogen originates in crop fields as applied fertilizer that exceeds plant uptake, percolating through tile drains into streams and thence into the Mississippi. The sheer geographical scale of the Mississippi watershed, stretching from Montana to New York, from Minnesota to Texas, encompassing approximately 40% of the contiguous United States, means that the river integrates water quality signals from across an entire continent. Attempts to reduce the Gulf of Mexico dead zone by cutting nitrogen loads in the Mississippi have confronted a fundamental structural challenge. The pollution sources are distributed across millions of individual farms over millions of square kilometers, each contributing a tiny fraction of the total load, none individually responsible for the problem downstream. Reducing that load requires not a single engineering solution but a transformation in agricultural practice across the entire American heartland. The rivers of Australia occupy a unique place in global hydrology because they are among the most hydrologically variable on Earth. Australian rivers, particularly those of the interior, can flow with great abundance for short periods and then remain dry for months or years. The Murray-Darling River system, which drains the southeastern quarter of the continent and is the primary water source for Australian agriculture, is characterized by extraordinary interannual variability driven by the El Niño Southern Oscillation. During El Niño years, when the Pacific Ocean's surface temperatures shift, rainfall across eastern Australia drops sharply, river flows plummet, and the Murray can slow to a barely perceptible trickle in its lower reaches. During La Nina years, floods of extraordinary scale sweep the floodplains. Australian freshwater organisms evolved in this regime of boom and bust, developing life history strategies of opportunistic reproduction during floods and deep dormancy during droughts. The Murray-Darling's overallocation to irrigation has severely reduced ecological flows, triggering crises including massive bird and fish kills during the extended drought of the early 2000s, stark evidence of the limits of treating river systems as purely utilitarian infrastructure. The rivers of Siberia drain approximately 10 million square kilometers of the world's largest landmass and collectively deliver an enormous volume of fresh water to the Arctic Ocean. The Ob, the Yenisei, and the Lena, three of the world's largest rivers by discharge, flow northward across the Siberian lowlands into seas covered with sea ice for much of the year. Their freshwater discharge dramatically reduces the salinity of the shallow Arctic shelf seas, contributing to sea ice formation by lowering the freezing threshold for surface water. Changes in the volume and timing of Siberian river discharge therefore have direct consequences for Arctic sea ice extent, which in turn affects global climate through changes in albedo, the reflectivity of the Earth's surface. Long-term discharge records show a significant increase in annual flows since the 1970s, consistent with increased precipitation and permafrost thaw as the region warms at 2 to 3 times the global average. As ancient organic carbon enters the river system through thawing permafrost, these northern waterways are becoming accelerating conduits transferring frozen carbon stores into the active climate cycle, a feedback that conventional models have historically underestimated. The permafrost rivers of Siberia and northern Canada offer a window into one of the most concerning feedback mechanisms in contemporary climate science. As permafrost thaws, it releases not only carbon stored in frozen organic matter but also ancient methane trapped in the ice itself, particularly from a substance called yodoma, an ice-rich permafrost type formed in Siberia during the last ice age. When thawing yodoma collapses into lakes and rivers, a process called thermokarst, it creates crater-like lakes called thermokarst lakes, and the organic matter it releases is decomposed by microbes in the anaerobic lake sediments, releasing methane directly into the atmosphere. Streams draining permafrost landscapes carry dissolved organic carbon at concentrations that are measurably increasing as warming accelerates thaw. When this ancient carbon, fixed from the atmosphere by plants thousands of years ago and frozen before it could be decomposed, enters rivers and is exposed to sunlight and microbial decomposition, it contributes to atmospheric carbon dioxide concentrations. The rivers of the high north are becoming conduits for the transfer of frozen carbon stores into the active carbon cycle, a process that has become a major and urgent focus of Arctic research programs worldwide. Ice itself transforms rivers in the high latitudes each winter into environments of extraordinary physical drama. When air temperatures drop below freezing, a river's water temperature falls toward zero, but flowing water resists freezing more effectively than still water. Before surface ice can form, the entire water column may supercool slightly, leading to the formation of frazzle ice, tiny, needle-like ice crystals suspended throughout the water that aggregate into pancake ice and eventually form a continuous ice cover. Beneath this surface ice, the river continues to flow, sometimes tearing the ice sheet and producing dynamic ice jams when sheets of ice pile up against bridges, bends, or shallow sections. Ice jam floods, which occur when an ice jam suddenly releases, sending a surge of water downstream, are among the most destructive and least predictable river floods in the cold regions of the world. In Siberia, Alaska, and Canada, entire settlements have been destroyed by ice jam floods that arrive with no warning during the spring breakup season. The Lena River's spring breakup, when ice disintegrates and drives downstream in a thunderous convoy of grinding flows, is one of the great dramatic natural events of the Amazon basin contains perhaps the world's most unusual geological feature associated with a river system, the Mantaro Landslide Dam, which in 1974 created a natural dam in the Peruvian Andes by blocking the Mantaro River, one of the Amazon's headwater tributaries. But more astonishing still is the geological evidence that the Amazon River itself once flowed westward, in the opposite direction from its current eastward course to the Atlantic. Geological reconstructions suggest that before the Andes began their rapid uplift approximately 15 million years ago, the river drained westward toward a shallow sea that occupied what is now the Amazon basin itself. As the Andes rose and blocked this westward drainage, the accumulated water eventually burst through the narrow barrier separating the basin from the Atlantic, reversing the entire river's direction. This reversal created what geologists call the transcontinental Amazon River as we know it today. Evidence for this reversal comes from fossil fish distributions, ancient marine sediments within the basin, and the remarkable presence of freshwater stingrays whose closest relatives are marine organisms that colonized the basin when it was still a shallow interior seaway. The ancient rivers of Mars represent one of the great unanswered questions in planetary science. Spacecraft imagery of the Martian surface reveals a planet scored by valley networks, outflow channels, and meandering features that are consistent with the action of flowing liquid water, most plausibly water, at some point in the planet's deep past. The valley networks, concentrated in the oldest Martian terrains, display branching drainage patterns remarkably similar to terrestrial river systems, suggesting that they were formed by precipitation and surface runoff rather than by other processes such as lava flow or wind erosion. The outflow channels, by contrast, are enormous. Some are tens of kilometers wide and hundreds of kilometers long, consistent with catastrophic flooding on a scale unimaginable on Earth, perhaps triggered by the melting of subsurface ice by volcanic heat. Isotopic measurements of Martian meteorites and data from the Perseverance rover's analysis of sedimentary rocks in Jezero crater suggest that water was present on the Martian surface during the Noachian period, roughly 4 billion years ago, for a duration of at least hundreds of thousands of years. Rivers on Earth have influenced human language, religion, philosophy, and mythology to a degree that no other natural feature can match. The word river itself derives from the Latin ripa, meaning bank, a shore defined by flow, and in dozens of languages, the names of rivers encode the oldest surviving vocabularies of human settlement. The Rhine, the Rhone, the Ren of medieval English, the Rin of Celtic languages, all derive from a Proto-Indo-European root meaning to flow, the same root that gives us the English run and the Sanskrit srava. The Ganges derives from gag, an ancient Sanskrit word possibly related to the Proto-Dravidian kaveri, meaning river. The Mesopotamian belief that civilization was born between rivers is mirrored in cultures across the world. In Hinduism, the confluence of rivers, the Sangam, carries special religious significance. The Prayagraj confluence of the Ganges, the Yamuna, and the mythical Sarasvati is considered the most sacred site in the Hindu cosmological geography. In ancient Egyptian religion, the Nile divided the world into the Kemet, the black fertile land of the living, and the Deshret, the red desert land of the dead, a cosmology written entirely. The future of rivers is inseparable from the future of humanity's relationship with climate, agriculture, energy, and urban growth. As the global population approaches 10 billion, the demands placed on river systems for water supply, food production, hydroelectric power, navigation, and waste disposal will only intensify. Meanwhile, climate change is altering precipitation patterns, glacier volumes, and extreme weather frequencies in ways that will transform the hydrological regimes of rivers on every continent. Some rivers will carry more water as warming increases precipitation in temperate and subarctic regions. Others will shrink as glaciers retreat and summer precipitation patterns shift. The timing of river flows will change as snowmelt occurs earlier in the spring, reducing summer flows in rivers that currently depend on gradual snowmelt to sustain them through the warm season. These changes will compound existing stresses from overextraction, pollution, and habitat modification. The rivers of the world, in their patient and relentless flow, carry within their currents not only water and sediment but the accumulated weight of every decision humanity has made about land, energy, and water, and every consequence of those decisions yet to arrive downstream. The mathematics of river networks carries a beauty that rewards careful attention. In 1945, the American hydrologist Robert Horton published a landmark analysis of stream networks, demonstrating that the number, length, and drainage area of stream channels within a watershed obey regular geometric progressions when arranged by order. A first-order stream is one with no tributaries. Two first-order streams join to form a second-order stream. Two second-order streams form a third order, and so on. The ratio of the number of streams of one order to the number of the next higher order, the bifurcation ratio, tends to fall between 3 and 5 across a wide range of river systems in different climates, geologies, and scales. This regularity, now known as Horton's laws, suggests that river networks self-organize into a scale-free structure governed by the same principles regardless of the size of the system. Ronald Shreve in 1966 showed these regularities could be derived from simple random branching assumptions, suggesting that river network architecture is not specifically tuned by geology but is the near-inevitable result of basic topological processes operating on any branching drainage system on any planet with gravity and a flowing fluid. The role of rivers in cycling carbon between the atmosphere and the ocean is a critical and still underestimated component of the global carbon budget. Rivers transport approximately 0.9 billion tons of carbon to the ocean each year, roughly 10% as much as the ocean absorbs directly from the atmosphere. This riverine carbon comes in two forms: dissolved inorganic carbon, derived from the weathering of carbonate and silicate rocks, and dissolved organic carbon, derived from the decomposition of plant material in soils. The weathering of silicate rocks, which consumes atmospheric carbon dioxide in a process that geochemists call the Urey reaction, converting it to bicarbonate ions that eventually reach the sea, is the long-term geological thermostat that has regulated Earth's atmospheric carbon dioxide concentration over hundreds of millions of years. Rivers are the delivery mechanism for this thermostat. Without rivers transporting weathering products to the sea, the calcium carbonate precipitation that eventually sequesters carbon from the ocean would not occur. In this profound sense, rivers are participants in the most fundamental chemical control system on Earth, the thermostat that has kept atmospheric carbon dioxide within the range compatible with complex life for 4 billion years. The ancient rivers of the Sahara are now buried beneath thousands of years of wind-blown sand, but their presence can be detected by satellite radar instruments that penetrate dry sediment to reveal ghost channels of rivers that once flowed across what is today the world's largest hot desert. These paleriver systems, most prominently the vast Megachad network in the south-central Sahara, were active during the African humid period, between roughly 11,000 and 5,000 years ago, when shifts in the Earth's orbital parameters intensified the West African monsoon and drove rainfall across much of North Africa. Lake Chad, today a fragment of its former self, was at its maximum extent an inland sea, Lake Megachad, covering approximately 400,000 square kilometers, larger than the present-day Caspian Sea. Rivers flowed northward from this lake system into what is now Libya, through landscapes supporting hippos, crocodiles, and human settlements now found only in the archaeological record. The transition to desert occurred in abrupt pulses, with early pastoral communities retreating eastward toward the remaining freshwater, ancestors of the peoples who would eventually organize civilization around the predictable floods of the Nile. The river systems of the Asian continent carry remarkable evidence of the geological youth of the Himalayas. One of the most striking features of Himalayan river geography is that some of the largest rivers, the Indus, the Brahmaputra, the Tsongpa, and the Sutlej, are antecedent rivers, meaning that they predate the mountains they now flow through. These rivers established their courses when the land was still flat, long before the collision of the Indian subcontinent with Asia began building the Tibetan Plateau, and they maintained their courses by eroding downward as the mountains rose around them, carving the world's deepest gorges in the process. The Indus River Gorge at Nanga Parbat in Pakistan is widely considered to be the world's deepest river gorge in terms of the relief between the river and the adjacent mountain summit. The river flows at roughly 1,000 meters above sea level while Nanga Parbat rises to 8,126 meters, creating a vertical relief of more than 7 kilometers. The rate of incision in some gorges exceeds 5 millimeters per year, a geologically extraordinary pace sustained not by any change in the river itself but by the inexorable rise of the mountains growing. Rivers serve as cultural boundaries as much as physical ones, and the history of human conflict over rivers is nearly as old as the rivers themselves. The Jordan River, flowing from Mount Hermon through the Sea of Galilee to the Dead Sea, is physically a modest stream. Its annual discharge is barely a fraction of the Thames, and its lower reaches are more trickle than river, yet it is among the most politically significant watercourses in the world. Its waters are divided between Israel, Jordan, and the Palestinian Authority under a series of historical agreements whose original allocations, made in the 1990s, are widely acknowledged to no longer reflect the hydrological realities of a region subject to population growth and climate-driven water scarcity. The Jordan today delivers almost no water to the Dead Sea, which has been shrinking at an alarming rate, roughly a meter of surface level per year, as upstream agriculture and municipal consumption have diverted essentially all of the river's natural flow. The shrinkage of the Dead Sea is one of the most dramatic examples of river overexploitation anywhere in the world, its fate entangled in the political complexities of one of the world's rivers collectively transport approximately 20 billion tons of sediment to the ocean each year, a figure that represents the aggregate result of all the rainfall, erosion, and transport processes operating within every watershed on Earth. This number is not constant. It has changed significantly over human history. Agricultural clearance, by increasing runoff and erosion from fields, dramatically increased sediment delivery from many watersheds beginning with the spread of farming. The construction of large dams in the 20th century then reversed this trend in many rivers, trapping sediment behind their walls and reducing the delivery of material to coasts and deltas. The net result of these two human interventions on global sediment flux remains contested, with different studies producing different conclusions depending on which rivers are examined and which time periods are compared. What is clear is that the natural sediment budget of the world's coasts, the balance between the material delivered by rivers and the erosion carried out by waves and currents, has been profoundly disrupted. Beaches naturally nourished by river sediment for thousands of years are now sediment-starved and eroding, a consequence that requires expensive artificial replenishment programs to simulate what healthy rivers once. The study of rivers has given human civilization some of its most powerful scientific frameworks. The concept of uniformitarianism, the principle that the same physical and chemical processes operating today also operated in the geological past, and that the present is the key to the past, was developed in part by observing rivers. James Hutton, the 18th century Scottish geologist often credited with founding modern geology, reached his revolutionary conclusion that the Earth was unimaginably old partly by observing river deposits and recognizing that their formation required far more time than the biblical chronology allowed. Charles Lyell elaborated these ideas in his landmark Principles of Geology, which became one of the most important influences on Charles Darwin's thinking about deep time and the pace of natural selection. The logic of uniformitarianism is, at its core, a logic derived from rivers. If a river erodes a millimeter of rock per century today, and the canyon before us is 1,000 meters deep, then the canyon must have taken 100 million years to form. This temporal vista, opened by observing rivers and their deposits, demolished young Earth cosmology and opened the vast horizon within which evolution and modern science would unfold. The future of hydroelectric power is being reshaped not only by the environmental critiques of large dams but by the emergence of new technologies that may eventually make some of the river system's energy available without any impoundment at all. Marine and river current turbines, devices that generate electricity from the kinetic energy of flowing water without requiring a dam or reservoir, are now being tested in several locations worldwide. Unlike tidal stream turbines, which harness the regular ebb and flow of tidal currents in coastal channels, river current turbines operate in freshwater environments, capturing the energy of persistent river flows in large, deep channels. The Mississippi River, the Congo, and the Amazon have all been proposed as suitable environments for in-stream current turbines at commercial scale, though the challenges of maintaining underwater mechanical equipment in rivers carrying abrasive sediment at high concentrations remain significant engineering obstacles. The energy density of flowing water, much higher than that of wind at any given current speed, means that relatively small turbines in fast-moving rivers could theoretically generate useful amounts of electricity with minimal surface footprint and no reservoir formation. There is something fundamentally instructive about water that has no choice but to find its way downhill. Rivers teach patience to those who study them, patience calibrated not in years or decades but in centuries and geological epochs. A river's response to disturbance is rarely immediate. Sediment disrupted upstream by a dam may take decades to work its way down to the coast. A species extirpated from one part of a river may recolonize from another if the connection is restored. A floodplain severed from its river by a levee may retain the ecological memory of inundation for 50 years in the seeds and root networks of its plants, awaiting a reconnection that may never come. Rivers also teach that boundaries drawn by human hands rarely correspond to natural units of management. A river does not know which state or nation it passes through, and the consequences of actions taken in one jurisdiction flow inevitably downstream to be received by communities and ecosystems that had no voice in the decisions that shaped them. Learning to manage rivers wisely under deep uncertainty, rather than pretending to certainty we do not possess, may be the defining challenge for freshwater science ahead. Beneath the surface of nearly every lowland river lies a world of extraordinary chemical activity that most observers never consider. The boundary layer between flowing water and the riverbed is not a simple line but a zone of perpetual transformation. Bacteria attached to sediment grains perform the work of denitrification, converting dissolved nitrate back into atmospheric nitrogen gas, removing a significant fraction of the agricultural nitrogen that rivers receive from their watersheds before it can reach the sea. Other microbial communities fix nitrogen, oxidize ammonia, and cycle phosphorus through a chain of biochemical reactions that collectively constitute the river's own internal metabolism. Scientists studying this metabolic activity have coined the term spiraling length to describe how nutrients travel downstream in a river. Rather than moving in a straight line, they cycle repeatedly between dissolved form in the water column and particulate form locked in biological tissue or sediment, spiraling slowly toward the sea with each cycle. In rivers with dense algal mats, abundant leaf litter, and complex hypereic zones, these spiraling lengths are short and nutrient processing is intense. The geomorphology of alluvial fans, the fan-shaped deposits that rivers build where they emerge from mountains onto flat plains, reveals much about the long-term behavior of mountain rivers and the hazards they pose to settlements. When a steep, sediment-laden mountain stream abruptly loses gradient at a valley mouth, its velocity drops and it deposits its load in a spreading cone of gravel, sand, and debris. Unlike meanders, which form through the gradual migration of a single channel, alluvial fans are built by rivers that shift their active channel frequently across the fan surface, abandoning one lobe when it clogs with sediment and switching to another. Entire cities in the arid American Southwest, Las Vegas, Salt Lake City, Tucson, are built on ancient alluvial fans. The streets and suburbs extending across these fan surfaces follow the topographic geometry of deposits laid down by rivers thousands of years ago. When extreme rainfall sends debris flows roaring down the mountains above these cities today, they follow the same geological logic as those ancient fan-building floods, preferentially occupying low points in the topography, which are often exactly where urban planners historically chose to build roads and drainage channels. The salmon of the North Pacific are among the most studied creatures in freshwater biology, not simply for their economic importance but for the astonishing physiological transformation they undergo between their saltwater and freshwater lives. A Pacific salmon, Chinook, sockeye, coho, pink, or chum, spends between 1 and 5 years in the ocean, growing large on a diet of fish and invertebrates, before its body undergoes a wholesale endocrine transformation that prepares it to survive in freshwater. The fish's kidneys, gills, and hormonal systems all shift to reverse the osmoregulatory strategy that sustained it at sea. Its metabolism redirects energy from growth to reproduction, and it stops eating entirely, surviving its entire upstream migration and reproductive effort on stored fat reserves. In streams where salmon populations are healthy, the collective biomass of spawning adults arriving each autumn represents an extraordinary pulse of marine-derived energy into the freshwater and riparian ecosystem. Researchers measuring the annual nutrient cycle in salmon streams have found that the autumn salmon run delivers more nitrogen to the riparian zone than the entire growing season's atmospheric deposition, fundamentally restructuring the productivity of the catchment for the following year. Flash floods in desert rivers represent one of the most dramatic and least predictable expressions of fluvial energy on Earth. In arid landscapes, soils are often poorly developed, vegetation is sparse, and rainfall events, though infrequent, can be intense and localized. A thunderstorm cell over a desert mountain range may drop several centimeters of rain within an hour over an area of a few square kilometers. The water cannot infiltrate the dry, compacted soil quickly enough and runs off almost immediately, converging in dry washes and canyons whose channels may not have carried water for months or years. Within minutes of the storm's onset, a wall of water and debris can be roaring down a desert canyon at speeds exceeding 8 meters per second, carrying boulders, uprooted trees, and sediment in a slurry of extraordinary destructive power. Hikers in slot canyons in the American Southwest, places like Antelope Canyon in Arizona, have been killed by flash floods that arrived under blue skies, generated by storms invisible beyond the canyon walls kilometers away. The flash flood is the desert's most unambiguous expression of the relationship between water and rock, brief, violent, indifferent to anything in its path. The history of river engineering is, in many ways, the history of civilization's ambition to eliminate uncertainty from the natural world. The Dutch, confronting a river delta environment of extraordinary instability, where the Rhine, Maas, and Scheldt emptied into the North Sea through a labyrinth of islands, tidal channels, and shifting sandbars, developed over 7 centuries an increasingly sophisticated system of dikes, sluices, polders, and eventually storm surge barriers that transformed their coastline from one of Europe's most flood-prone into one of its most controlled. The Delta Works, completed with the Maeslantkering storm surge barrier in 1997, represents the apex of this engineering tradition, a set of movable barriers capable of closing off the Rhine-Maas Delta from North Sea storm surges while remaining open for normal shipping traffic. The Dutch relationship with their rivers and the sea has generated an entire culture of water management exported globally, with Dutch engineers and consultants involved in flood control and water management projects from Bangladesh to New Orleans. Even the Netherlands, with unparalleled engineering expertise, is rethinking its strategy in the face of sea level rise, acknowledging that some areas may ultimately need to be returned to the sea rather. The role of rivers in the formation of coal has been underappreciated in most popular accounts of energy history. The vast coal deposits of the Carboniferous period, roughly 350 to 300 million years ago, were formed primarily from the remains of trees and other vegetation that grew in coastal and deltaic swamp forests and were periodically buried by river floods, then compressed over millions of years into the black carbon seams that powered the Industrial Revolution. The rivers of the Carboniferous differed from modern rivers in one critical respect. The bacteria and fungi capable of efficiently decomposing lignin, the tough structural polymer that gave Carboniferous trees their rigidity, had not yet evolved. Trees fell, accumulated in the swamps beside their rivers, and instead of rotting were buried by flood sediments and preserved. The coal measures of England, Wales, Pennsylvania, the Ruhr Valley, and Silesia are thus the fossilized floodplains of ancient rivers. The energy extracted from those seams was sunlight captured by Carboniferous trees, deposited by rivers that flowed when continents were arranged entirely differently before the first reptile had laid an amniotic egg on the Paleozoic floodplains of the ancient world. Water temperature is one of the most consequential physical properties of a river, governing the rate of every chemical reaction within it, the solubility of oxygen, the metabolic rates of every organism, and the viability of temperature-sensitive species. Cold water fish like trout and salmon require dissolved oxygen concentrations that are only achievable in cool water. As temperature rises, oxygen solubility declines and their physiological tolerance is exceeded. Riparian shade is thus not merely a comfort for stream ecology but a thermal necessity. Studies in Oregon streams have demonstrated that removing streamside trees can raise summer water temperatures by as much as 8 degrees Celsius, the difference between a stream capable of supporting summer salmon rearing and one that is lethal to juvenile fish. Climate change is compounding this problem by raising air temperatures and reducing the snowpack that moderates summer river flows, causing many montane streams to run warmer and lower simultaneously. Thermal refugia, cold water springs, tributary confluences, and deep pools where groundwater seeps maintain low temperatures, are becoming increasingly important as climate-driven warming pushes river temperatures toward biological thresholds. The rivers of tropical Africa contain one of the strangest biological guilds on Earth, the electric fish. Both the weakly electric mormyrids, which generate low-voltage fields for navigation and communication, and the strongly electric catfish, Malapterurus electricus, capable of discharging up to 450 volts, inhabit the river systems of sub-Saharan Africa. The mormyrids, a family of over 200 species found almost exclusively in African rivers, have evolved one of the largest brain-to-body ratios of any fish, driven by the neural demands of processing electrosensory information in the murky, sediment-laden waters they inhabit. Each mormyrid species produces an electric organ discharge of a characteristic pulse pattern and frequency, and individuals can distinguish the discharges of conspecifics from those of other species with extraordinary precision, using these signals for mate recognition and territorial signaling in conditions of near-zero visibility. The evolution of electrosensory systems in these fish is one of the most compelling examples of sensory evolution driven by the specific physical properties of a river environment, the electrical conductivity of the water, its turbidity, and the demands of nocturnal activity in a habitat where vision offers almost no useful information. The springs that feed rivers, the points where groundwater emerges at the surface, are ecosystems in their own right, possessing unique biological communities shaped by the constancy of their physical conditions. A true spring, unlike a surface stream, maintains nearly constant temperature year-round, reflecting the mean annual temperature of the surrounding groundwater rather than the fluctuating air temperature above. In temperate regions, springs are warm in winter and cold in summer relative to adjacent streams, creating thermal refugia for aquatic organisms at the extremes of both seasons. Spring-fed streams in Florida and other karst regions of the American South maintain water temperatures so constant, typically hovering near 20 degrees Celsius regardless of season, that they support unique communities of aquatic plants, invertebrates, and fish found nowhere else. The Florida springs also harbor wintering populations of West Indian manatees, large marine mammals that congregate in the warm, clear spring outflows each winter when Gulf of Mexico water temperatures drop below their thermal tolerance. The spring's constancy, a product of the vast heat buffering capacity of the groundwater aquifer, sustains these communities through temperature extremes that would be lethal in normal surface streams. The concept of the river continuum, proposed by Robin van Noot and colleagues in a landmark 1980 paper, transformed freshwater ecology by providing a unified framework for understanding how biological communities change along the length of a river from headwaters to mouth. In the headwater reaches, small, shaded, tumbling over rocks, the river receives abundant inputs of leaves and woody debris from the surrounding forest but produces little photosynthesis itself because the tree canopy blocks sunlight. Organisms here are dominated by shredders, invertebrates that break down coarse leaf litter into fine particles. As the river widens downstream and the canopy opens, sunlight reaches the water surface, algae and aquatic plants establish, and the community shifts toward grazers feeding on attached algae and collectors processing the fine organic particles drifting downstream from the headwaters. In the lower, larger reaches, turbidity increases, light penetration decreases, and organisms depend primarily on fine organic matter transported from upstream, shifting the community again toward collectors and filter feeders. The framework has required significant modification when applied to tropical rivers, heavily impacted systems, or rivers with major groundwater inputs that disrupt the expected longitudinal patterns of biological community structure. The Okavango River of southern Africa achieves something almost paradoxical. Instead of flowing to the sea, it flows into the middle of a desert and disappears. Rising in the highlands of Angola as the Kubango River, it flows southeast through Namibia and then into the Kalahari Desert of Botswana, where it spreads across the Okavango Delta, the world's largest inland delta, before its waters evaporate and transpire without ever reaching any ocean. The delta it creates covers approximately 15,000 square kilometers during peak flood, a shifting mosaic of permanent water, seasonal floodplains, and dry land that constitutes one of the most pristine and biodiverse ecosystems in Africa, inscribed as a UNESCO World Heritage Site in 2014. The flood that sustains the Okavango Delta arrives paradoxically during Botswana's dry season, because the pulse of rainfall in the Angolan highlands takes several months to travel down the river and spread across the delta. Elephants, hippos, lions, African wild dogs, and an extraordinary diversity of waterbirds depend on this precisely timed annual inundation. Because the Okavango flows through 3 nations, its continued integrity depends on transboundary cooperation that remains fragile as upstream water demands grow steadily with population. The physics of a river in flood is categorically different from the physics of the same river at normal flow, not merely in scale but in fundamental character. As a river rises above its bankfull stage and water spills across the floodplain, the flow encounters a sudden and dramatic increase in resistance from vegetation, soil roughness, and the irregular topography of the floodplain surface. The floodwater slows dramatically as it spreads, losing its sediment-carrying capacity and depositing the fine silts and clays that historically built some of the world's most productive agricultural soils. This deposition is not random. Immediately adjacent to the channel, where floodwaters first slow, coarser sediments settle out to form natural levees. Further onto the floodplain, only the finest particles remain in suspension, settling as they travel to create the characteristic horizontal layering of floodplain stratigraphy. Floodplain sediment profiles thus preserve a laminated record of individual flood events, readable by geologists and geomorphologists as a stratigraphic archive. Floodplain sediment profiles thus preserve a laminated record of individual flood events, readable as a stratigraphic archive, allowing researchers to reconstruct flood histories extending centuries beyond the short instrumental record. The question of what a river will look like in 100 years from now is among the most consequential and most difficult in environmental science. Climate projections agree on the direction of change in broad terms: a wetter atmosphere carrying more moisture globally, but with that moisture distributed more unevenly, delivering heavier rainfall events punctuated by longer droughts, but disagree substantially on the regional specifics that matter most for river management. In the Colorado Basin, the Nile watershed, the Murray-Darling system, and the Yellow River, all already under extreme human pressure, the combination of reduced flows and increased demand is widely projected to create crises of water supply within the lifetimes of people now living. In other systems, the challenge will be managing larger and more frequent floods in landscapes where floodplains have been converted to agriculture and cities. The most honest answer that hydrology can offer to questions about rivers' futures is not a specific prediction but a set of probabilities and thresholds, a language of uncertainty that sits uneasily with the certainties that infrastructure planners, politicians, and farmers require to make decisions.